SwayamPrabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as Professor, Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The topic of today's lecture is resource allocation in MEC. Resource allocation in MEC, the full form of MEC is mobile edge computing. So, what do we mean by the resource allocation in mobile edge computing? This refers to the process of distributing computing resources such as CPU, memory, storage and network bandwidth among different applications or the services that are running on the edge servers. Now, we have to understand that the concept goes like this. This is the user equipment, this may be a smartphone which is a mobile device, and then you have the cellular base stations, and these cellular base stations are now having the connectivity of edge data centers, or you also say that it is an edge cloud. And then using long haul they are connected with the cloud. So, edge cloud positioning for mobile communication, that is the edge computing for mobile networks, we call it as mobile edge computing. Now, there may be many user equipments which are running different applications, they are called mobile applications, and to support these mobile applications which requires lot of resources such as more of CPU, more of memory, more of storage and network bandwidth, which otherwise is not available. So, what they will do? They will, with the help of technology MEC, they will be running this application with the help of edge data center or edge computing, and therefore, it is called mobile edge computing. So, in other words, it is an edge computing for mobile networks, which are also popularly known as cellular network. Let us get started again by understanding the resource allocation in mobile edge computing. So, resource allocation in mobile edge computing refers to the process of distributing computing resources such as compute, memory, storage and network among different applications or the services that are running on the mobile edge servers. This MEC enables the mobile devices to offload their compute intensive task to the edge servers. They are called the edge servers. Located close to the network edge, here we are calling it as base station, very close by to the base station, which can improve the performance of applications and reduce the network latency. So, two important things why we need for this particular help from the edge computing is to offload these compute intensive tasks to the edge servers, which are located, which can improve the performance of the applications. Application performance is one criteria. Second is it will reduce the network latency. Now, to achieve this, mobile edge computing system needs to manage the available resources efficiently and allocate them to the applications in a way that maximizes the overall system performance. So, this becomes an optimization problem that how it is going to allocate the resources over billions of user equipment that is most important, which are running different applications. Unless this allocation of resources is efficiently done, it will not be possible to accommodate all the requests of user equipments. So, therefore, resource allocation in MEC becomes quite important. So, resource allocation in MEC can be the dynamic and adaptive, taking into account the factors such as the current load at the edge server and the quality of service requirement of the application and the available network bandwidth. So, these are three important features or parameters which is required for resource allocation in MEC. Now, these can be either static means it can be decided beforehand, or it can be dynamic, that is keeps on changing different requirements, and this kind of resource allocation strategy also is dynamically computed. But in all the cases, these three different factors are very much needed, called features, to find out this resource allocation in MEC. They are the current workload of the edge server. We mean that the availability and the use of the edge servers, that is availability and use of the current use of the edge server means that what are the resources which are available and how much they are going to be used in further future of time. Another important thing is the quality of service requirements of these particular applications. And third important thing is available network bandwidth, so that these particular offloading or the resource allocation in MEC, which is nothing but to offload these compute intensive tasks to the edge server, can happen. So, the goal is to ensure the resources are utilized optimally while meeting the delay constraints of the application and minimizing the overall energy consumption of the system. Why this energy consumption is the important criteria in the mobile edge computing? Because once the user equipment they offload their task to the edge server, they can save the remaining energy of that mobile phone. It can live longer before it can be recharged again. So, overall minimizing such overall energy consumption is also one of the objectives of the resource allocation in MEC, and another constraint is about the delay constraint of the application. So, all the applications have their constraints of delays. So, how much delay it can tolerate by the application is an important criteria for resource allocation into this particular system. Having understood the requirement or the features of resource allocation in MEC, let us go ahead getting into more details. So, resource allocation in MEC, that is nothing but the decision on full or partial offloading. So, full offloading and partial offloading of an application to the MEC. This particular aspect, whether the application, whether this particular application which is running on the mobile phone, that is the user equipment, is fully offloaded, that means everything to be done with the edge server, not in the mobile phone, or it is a partially one, that means some part will be offloaded to the MEC, and that is for the edge server to compute, and remaining will be happening over there in the mobile user equipment. So, that particular decision on whether to go for the full offloading or partial offloading of an application to the MEC is accompanied by the proper allocation of computing resources on the edge servers, that is the edge nodes, and if they are not met by that requirement of the application is not met by the edge server resources, then the cloud as well can be thought as the alternative means of offloading the applications for providing the computational resources to the applications. Therefore, the selection of computation placement, whether it is influenced by the ability of offloaded application to be parallelized or partitioned. So, meaning to say that to understand this important concept, that selection of computation placement means that out of this full or partial offloading, whether it is to be done where in which part, whether user equipment, if it is saying that partial means some part will be executing in the user equipment, when you say full means everything will be offloaded, that means user equipment, that is the mobile phone, is not able to provide the resources. So, it is offloading all its application execution over either the edge nodes, but in which of the edge nodes, otherwise the cloud. So, this is the selection whether it is to be done on user equipment or it is to be done on the edge node or it is to be done on the cloud. So, this particular choice, that is called the placement, computation placement. So, it has to be a selection of computation placement, and this particular selection of computation placement is influenced by the ability of the offloaded application, whether it can be partitioned or it can run in a parallel mode or not. So, let us go ahead in understanding about this aspect, that ability of offloaded to be partitioned or parallelized or not. If it is if the parallelization or partitioning of the application is not possible, let us see the example that if let us say the any mobile application has a particular module which takes the input from the user. Let us say that user is typing some input. So, that part is not offloadable or is not partitioned, but remaining computation part of that application can be partitioned or it can run in one of these placements, that is whether it can run on the edge or on the cloud. So, the parallelization and the partitioning of the application is not possible. If it is not possible, then only one physical node may be allocated for the computing, since the application cannot be split into the parts. On the opposite side, the offloaded application may be processed by the resources distributed over several computing nodes. This is explained here through an example. So, in this example you can see that this is the user equipment 1 and its requirements of the application. Now, similarly you can see that user equipment 2 and its requirement of the application for the computing needs. Now, these applications whether can be partitioned or not, here let us say that here it is partitioned. Partition in the sense you can see that this application has 3 different modules 1, 2 and 3, whereas this user equipment has the application which cannot be partitioned and it can run as a whole application. So, what will happen if it is not partitioned or it is not partitionable? So, parallelization is not possible over here. So, only one node, physical node may be allocated for the computing. Let us say that this particular user equipment 1 want to offload its compute, then it will be offloaded in entirety to one of these base or edge servers, which is inside the NEC. So, you can see that this entire application will be offloaded in its entirety here in ENB1 edge server, and this will be running as the virtual machine, that is shown over here. So, they are called offloaded application. So, this offloaded application is from user equipment 1. So, this part offloads the whole application to ENB, as this application cannot be partitioned, that we have already explained. The second part of this example says that the application offloaded by user equipment 2 can be partitioned. So, here you can see that this particular application is partitioned into 3 different modules, and therefore, it can be partitioned, and the resources are allocated from all 3 ENBs. So, we are going for the example of parallelization. So, when you say parallelization, means all its component of that application will simultaneously be executing. Let us say that one is executing on ENB 1 of user equipment 2, the second component of this particular user equipment 2 will be executing on ENB 3 as the virtual machine, and the third one will be executed on ENB 2. So, you can see that when they are executed, they are to be executed in parallel. So, therefore, that execution time also will be reduced by 1/3 here in case of user equipment 2, whereas this particular time is still, if let us say the application, if it is able to be split, then it is possible to reduce the time further. So, this is an example of the method which, let us summarize this, that this scheme, what we are going to say, that in the resource allocation we are going to see whether how this selection of computation placement is going to happen. Computation placement is dependent on whether the applications is partitioning, the ability to partition or not. So, if they are partitionable, then it can execute in parallel, then it may possible to execute in parallel. If it is not partitionable, then only one node, that is one edge node, it can be offloaded to. So, this is what we have seen here in this particular slide. So, that is one of the requirements, that is called the selection of computation placement in the resource allocation. Now, let us see some more details that about the resource allocation. So, the main objective of the resource allocation problems in MEC, that is mobile edge computing, is the maximization of the amount of applications served by MEC while satisfying the delay requirements of the offloaded applications and optionally the energy consumption of the particular system. So, this becomes the main objective, that overall how to maximize the amount of applications which are being served by MEC. So, from the MEC angle, from MEC perspective, the main objective of the resource allocation to the different application is how to maximize this amount of applications served by MEC while satisfying the delay constraints of the offloaded applications and optionally the energy consumption of the particular system. The decision where the individual application should be placed, that is the selection of the placement, depends on the application priorities, applications delay requirements and the availability of the computing resources at the MEC. So, there are two ends, one is the application, the other end is the MEC, that is the edge servers. So, these two parts that will be the decision making, the applications delay requirements and the availability of computing resources at. So, these two important things together will decide the individual applications placements on the application priorities. Now, offloaded applications are firstly delivered to the local scheduler. So, here you can see in this example, see this user equipment, this has the application to be processed. So, what it will do? It will first give it to the scheduler. So, the offloaded applications are firstly delivered to the local scheduler with the MEC, and the scheduler checks if the computing node with the sufficient computation resources have exist or not. So, if there is a computing node with enough of the resources such as virtual machines are allocated to the nodes. So, here the resources of the edge computing or the edge node is virtualized. So, this is the edge node with the virtualization enabled, so that the resources are allocated in the form of virtual machines. Then the applications is processed at this MEC node and the results are sent back to the UAV, to the UE. So, you can see that once the VMs are allocated to that particular user equipment's application, it will be computed and the results will be returned back to the user equipment. If the computation power provided by MEC is not sufficient, the scheduler delegates the application to the cloud. So, you can see that the scheduler decides both whether the sufficient requirement of resources is available with the edge node, then it will schedule over there as a first priority, otherwise it will be scheduled to the cloud, centralized cloud. If let us say the requirement of the resources is beyond than the available with the edge nodes, then it will be transferred to the cloud. So, this is called, this example shows you the placement of resources, computing resources, that is whether it is to be at the edge node or it is to be at the cloud. Now, let us see the application assignment index. The application assignment index policy is a mechanism for application placement and the resource allocation in mobile edge computing. So, it is used to decide which application should be assigned to which edge server based on the several factors, such as the computational requirement of the application, then network latency, then available resources and the quality of service requirement of the application. So, these are several factors which require to decide which application should be assigned to which edge server. So, it is called a matching based on these factors. On one side it is the applications, the other side it is the edge servers. So, the applications with these requirements 1, 2, 3, 4, except this one. So, 1, 2 and 4 are the factors of the application, whereas available resources, that is 3, is a factor of H server. Together these two factors will perform the matching, and this matching is called the assignment. So, application assignment index policy involves assigning an index to each application based on its resource requirement and QoS requirement. So, this particular 3 factors, that is computational requirement, network latency and quality of service, will make an AAI policy, and this particular policy will be based on will then ensure that each application based on this resource requirement and quality of service constraints are being satisfied or met. So, therefore, this particular index is a scalar value that indicates the suitability of an application for the deployment on a particular edge server. So, this is going to be an important index here. So, the edge server with the lowest AAI index is selected as the destination server for that particular application. So, once this particular application assignment index is computed, then the lowest of this application assignment index is selected as the destination server for that application. So, application assignment index can be calculated based on the various factors such as the CPU memory requirement of an application, available bandwidth and the network latency between the edge server and the user devices. In addition, the quality of service requirement of an application such as response time, availability and reliability can also be incorporated in application assignment index calculation. So, the application assignment index policy is particularly useful in the scenarios where multiple applications are running on multiple edge servers and the system needs to decide how to assign the resources to different applications in a way that maximizes the overall system performance. By using application assignment index, the MEC can allocate the resources in a dynamic and adaptive manner based on changing workloads and QoS requirement of the application and optimize the utilization of edge resources. Now, let us see simple example for calculating the application assignment index. So, let us assume that we have two edge servers, server A and server B. And server B. And the two applications, let us say app 1 and app 2, that need to be deployed on these particular servers running on the different user equipments 1 and user equipment 2. Now, the applications have different computational requirement and QoS constraints. For example, application 1 requires 2 CPU cores, 4 GB of memory and has a response time requirement of 50 milliseconds. Application 2 requires 1 CPU core, 2 GB of memory and has a response time equivalent to the 100 milliseconds. So, let us see the AAI calculation, that is application assignment index calculation, can be performed as follows. So, in step 1 we have to calculate the resource requirement of each application on each server, assuming that each server has 4 CPU cores and 8 GB of. So, this has 4 CPU core and 8 GB of memory. This also has 4 CPU core and 8 GB memory. So, the application 1 on server A the resource utilization would be 2 by 4. So, here for application 1 the resource utilization would be 2 by 4 plus 4 by 8. So, 2 and 4 they are the requirement of application 1 and that becomes 1, whereas application 1 on server 2 requires 2 by 4, again the same thing in B also, that is equal to 1. Application 2 on server 1 it requires 1 by 4 plus 2 by 8, that becomes 0.5. Whereas application 2 on server B requires again 0.5. Let us calculate the latency between the edge server and the user devices, assuming that the latency between the server A and the user device is 50 and the latency B from the user device is 25. And then calculate the AI index for each application on each server using the formula that application assignment index is equal to W1 multiplied by resource utilization plus W2 into latency plus W3 into QoS requirement, where W1, W2 and W3 are the weight factors that determine the importance of each factor in AI calculation, assuming that the weight factors are 0.5 to prioritize the resource utilization, 0.3 to consider the latency and 0.2 to consider the resource QoS requirement. So, AI calculation for each application on each server can be performed as follows. So, AI for application 1 on server A will give you the total AI index of 25.3, where AI for application 1 on server B will become 40.5, AI for application server on server A is 35.25, AI for application 2 will become 27.75. So, based on these AI values, the MEC would assign application 1 to the server A. So, this becomes the lowest, hence this assignment, that is for the application 1 will be assigned to the server A, which is the lowest of AI index of 25.3, whereas app 2 will be application 2 will be assigned to the server B. Why? Because for server B it is the lowest one compared to the other assignments, which has the lowest index, that is 27.75. This ensures that the applications are assigned to the edge servers that can provide the necessary resources and meet the quality of service requirement while optimizing the utilization of the edge resources. Now, resource allocation in MEC, we will see some more details. So, in case of VM based resources that we have seen in the previous slide, the resource allocation problem has to deal with the minimization of execution delay of the offloaded application, along with the minimization both the communication and computing resource overloading or over provisioning and virtual machine migration cost. So, the computing nodes are responsible or represented, the computing nodes are represented by SCENB, and the VM migration may be initiated due to SCENB's shutdown. So, that is one case. The whole problem can be formulated as the VM allocation at SCENB and solved by means of Markov decision process, that is MDP. For example, the virtual machine for UE1 is allocated at the serving SCENB1 that we have seen, while user equipment 2 has allocated the virtual machine at the neighboring SCENB3. These two things are shown. Now, SCENB3 is preferred because the high quality backhaul backhaul resulting in low transmission delay of the offloaded application. So, it is called as a low delay. With the higher VM migration cost, the VM is preferred to be allocated at the serving SCENB, that is SCENB closest to the UAV, if this SCENB has enough computing power. Now, forming clustered resource allocation. Now, forming the clusters of SCENB is a common approach to optimize the resource allocation in mobile edge computing systems. So, let us see about this particular another requirement. So, the clustering involves the grouping together the set of SCENBs that are geographically close to each other and can be controlled and managed as a single unit. So, this we are showing through this particular capture that this is a cluster and this particular cluster has the SCENB1 and SCENB2 and SCENB3, 3 different clusters. Now, forming clusters, the MEC system can effectively manage the resource allocation among SCENBs and improve the overall performance of the system. That is quite obvious through the example. Let us go ahead. So, the allocation of computing resources is done as follows. Firstly, the serving SCENB try to serve their user equipment on its own, since this results in a short communication delay. So, for example, here SCENB1 allocates the computing resources to UAV to UE1 and UE2. So, you can see that this SCENB1 this allocates 2 VMs, one is to the UE1 and the other one is to UE2. Only if SCENB is not able to process the application on its own, it is forwarded to all SCENBs in the same cluster. So, here the computation for UE3 is done at SCENB2. So, you can see that this particular UE3 computation is done on different SCENB2. So, the computation of user equipment 3 is done at SCENB2 and SCENB3. So, it has another computation will be done here in SCENB3. So, this is an advantage of a clustered resource allocation. Now, let us see about the clustered resource allocation, that is the steps to form the clusters of SCENB for resource allocation in MEC. So, first step is to identify the SCENBs, that is to identify the set of SCENB in the network that are available for clustering. Then second is define the clustering criteria, that is define the criteria for clustering such as proximity of SCENBs to each other, network load, available resources and QoS requirement of the applications. Third thing is that to determine the cluster size, that is determine the optimal cluster size based on the clustering criteria. So, the cluster size can be determined based on the number of SCENBs that can be controlled and managed effectively as a single unit. So, the cluster size may determine dynamically as well. Now, then form a clusters, that is from the clusters based on the clustering criteria and cluster size. So, each cluster should contain the set of geographically close SCENBs that can be managed together as a single unit. Assign the resources. Once the clusters are formed, the MEC system can allocate the resources to each cluster based on the available resources and the QoS requirement of the application. This can be done using various resource allocation techniques such as dynamic resource allocation, load balancing and QoS based resource allocation. Then finally, the monitoring and optimization. Finally, MEC should continuously monitor the performance of the cluster and optimize the resource allocation based on changing workloads and QoS requirement of the application. Now, by forming the clusters of SCENBs, the MEC system can effectively manage the resource allocation among SCENBs and improve the overall performance of the system. That can lead to the reduced network latency, improved application response time and better utilization of edge resources. So, let us summarize this particular slide before we go ahead. This is an important notion of introducing the clustering. Of SCENBs for efficient resource allocation, that is in MEC to effectively manage resource allocation and thereby improving the performance of overall system. So, that means the clustering requires the following criteria. So, the criteria such that the proximity of SCENBs to each other, the network load, available resources, QoS requirements of the application. Then it will determine the cluster size and then it will form the clusters and then assign the resources. Resource allocation is done using the techniques called as a dynamic resource allocation, load balancing and QoS aware resource allocation. Then it will also enable to monitor the performance. So, clustering has so many advantages that overall performance of the system is under the control and thereby it can lead to the reduced latency, improved application response and better utilization of resources. These are the advantages. So, advantages are the following. One is the reduced network latency. Second advantage of clustering resource allocation is improved application response. Third advantage here is better utilization of edge resources. Now, coming up with the next important step, that is called the selection of compute node. So, the selection of compute node can significantly influence not only the execution delay, but also the power consumption of these computing nodes. So, the following key observations are made in this regard to the impact of cluster size, the amount of SCENBs performing the computing on both reducing the network on executing or execution latency of the offloaded application and the power consumption of the SCENBs. So, therefore, let us see these criteria. Let us say that backhaul topology, fully mesh topology combined with the fiber or the microwave connection is the most profitable in terms of execution latency when compared to the ring and tree topology. Backhaul connection, fiber backhaul in the ring topology results in the lowest power consumption over microwave and LT based connections. Third one is the number of nodes. Increasing the number of nodes of the computing SCENBs does not always shorten the execution delay. If a lot of SCENBs process the offloaded applications and the transmission delay become longer than the computing delay at SCENBs, the execution delay may be increased instead. So, with an increasing the number of computing SCENBs, power consumption increases as well. So, a proper cluster formation and SCENBs selection plays a crucial role in the system performance monitoring. So, the problem to find the optimal formation of clusters of SCENBs for computation taking into account both execution delay and the power consumption of the computing node becomes important consideration. So, clustering strategies in MEC. So, clustering strategies means selection of computing nodes. For a selection can significantly influence not only execution delay, but also the power consumption of the computing node. So, in such cases the optimal formation of clusters of SCENBs for computation taking into account both execution delay and power is required. So, the first clustering strategy, that is SCENBs, are selected in order to minimize the execution delay. Since all the SCENBs in the system are assumed to be one hop away, that is, we are considering the full mesh topology. So, all the SCENBs are included in the computation offloading and resource allocation. This can significantly reduce the execution delay due to the fact that the computation gain that is increased in the offloading application processing is far greater than the transmission delay. This is the first strategy of clustering strategy. The second objective, the objective of the second clustering strategy is to minimize the overall power consumption of the cluster. So, in this case only the serving SCENBs is preferred to compute. Thus, any computation at the neighboring SCENBs is suppressed to minimize the power consumption of SCENBs. This, however, increases the overall latency, the high variation of the computation load, but nevertheless it will minimize the overall power consumption of the cluster. Last clustering strategy aims to minimize the power consumption of each SCENBs in the cluster, since the power consumption of individual SCENBs is highly imbalanced in the second strategy. So, the cluster allocation refers to the process of assigning clusters of SCENBs to UE. So, multi-UE scenarios where the SUE is about to offload the data to the computation for the computation and the computing is assigned to it. Consequently, each user equipment has assigned different cluster size depending on the application and user equipment's requirement. So, the main objective in this case is to minimize the power consumption of the cluster while guaranteeing required execution delay for each UE. So, some cluster allocation strategies will include successive cluster optimization. So, the main objective of successive cluster optimization is to improve the performance of MEC system by dynamically adjusting the cluster size and resource allocation based on changing workload and QoS requirement of the application. In successive cluster optimization process, the MEC can split a cluster into a smaller clusters if the cluster is becoming overloaded, or merge smaller cluster into the large clusters if the clusters are underutilized. So, this adjustment of cluster size allows the MEC to allocate the resources more efficiently than among the clusters. Joint cluster optimization core idea is to jointly compute the clusters for all active users requests simultaneously to being able efficiently distribute computation and communication resources among the user equipment and to achieve higher quality of service. So, the main objective is to minimize the power consumption of clusters while guaranteeing the required execution delay. Now, static clustering. In a static clustering approach, once the clusters are formed, the allocation of the resources among the clusters remain static and does not change based on changing workloads and the QoS requirement of the application. Usually, the resources are divided equally among all SCENBs. Static clustering has the advantage of simplicity and ease of implementation. However, it may not be suitable for MEC with a highly dynamic workloads and QoS requirements, as the static allocation of the resources may result in the underutilization and overutilization of the resources. Now, balancing of communication and computation load. So, the allocation of computing resources not only requires to minimize the execution delay and or power consumption of the computing node, but also to avoid the unequal load distribution among the individual computing nodes, which may result in a backhaul overloading. Hence, the balancing of communication and computation load of SCENBs while satisfying the delay requirement of the offloaded application is needed to avoid unequal load distribution and backhaul overloading scenarios. So, the application considering algorithm, that is ACA, can be used in such cases for selecting suitable SCENBs according to the current computation and communication load of SCENBs. So, the ACA algorithm exploits the knowledge of the overloaded applications requirement, such as number of bytes to be transferred and the maximum latency acceptable by the application or the user. So, the selection of SCENBs for the computation is done in a static way prior to the offloading to avoid the expensive virtual machine migration. Now, let us consider the mobility management in MEC. In the conventional mobile cellular networks, the mobility of the users is enabled by handover procedure. When the user equipment changes the serving ENB or SCNB, as it roams throughout the network to guarantee the service continuity and QoS requirement. So, if the UE offloads the computation to MEC, it is important to ensure the service continuity. There are several solutions that mobility of user equipments. The first is low mobility user equipment. So, to adopt the transmission power of ENBs and SCENBs during the time when offloaded application is processed by MEC, the example of a low mobility is that moving inside a room. High mobility user equipment, that if the user equipment performs handover to the new serving ENB or SCNB despite of the power control, the service continuity may guarantee either by the virtual machine migration, that is the process during which the virtual machine runs at the current computing node is migrated to another one and more suitable the computing nodes, or by selecting of a new communication path between UE and the computing node. VM migration. If the UE's mobility is not limited and the power control is no longer sufficient to keep the UE at the same serving ENB oblique SCENBs, a possibility to initiate the VM migration should be contemplated in order to guarantee the service continuity and QoS requirement. On one hand, the VM migration has its cost, that is called cost M, representing the time required for VM migration and backhaul resources spent by transmission of VMs between the computing loads. On the other hand, there is a gain if VM migration is initiated called gain of M, since the user equipments can experience a lower latency and backhaul resources do not have allocated for transmission of computation results back to the UEs. Now, without VM migration, a probability that UE is connected to the optimal MEC decreases with the increasing number of hops between the UE and ENB where the service is initially placed. We are concluding this particular lecture. Thank you.